So now we give a characterization of the hyperbolic plane in terms of its discriminant. Obviously, the discriminant of the hyperbolic plane is -1. Now we show that the converse is actually true. If we have a binary quadratic space and its discriminant is -1, then it must be isometric to the hyperbolic plane. So let's see why that is. Suppose that the discriminant of v is -1. We're gonna prove that v is isometric to the hyperbolic plane in 2 steps. First, we show that v must be isometric to a space of this form. And then we show that such a space must be isomorphic to a space with the following gram matrix. And this clearly is isometric to the hyperbolic plane. Alright, so let's start with assuming that the discriminant of v is -1, and we want to show that v is isometric to a space of this form. Now, because v is a quadratic space, we know that in some bases, v is going to be isometric to a space like this. That means that the gram matrix of v is of this form. But remember that this alpha and beta are only defined up to a square in f star. Why is that? Well, because let's say v is isometric to this in v1, v2, that would just mean that in particular we have that bv1, v1 is alpha, bv2, v2 is beta. If I shrink v1 by a constant, then this bv1 cv1 over c, that whole thing is going to be shrunk by c squared, so this become alpha over c squared. So changing alpha and beta by a square does not change the isometry class of v. Thus now it remains to show that up to a square, beta is equal to minus alpha. And that just comes from the assumption that this discriminant is -1. So alpha beta is -1. Beta is -1 over alpha in f star up to f star square, and -1 over alpha is just minus alpha. Where's that? So in modulo f star square, -1 is just minus of alpha square. Right, so alpha beta is equal to minus alpha square, and so beta must be congruent to minus alpha mod f star square. So we see that v must be isometric to this space. So now we want to show that this space is isometric to a space with this gram matrix, and then this clearly is isometric to the hyperbolic plane. So why is that? So let's say v is isometric to this space in the spaces v and w. We claim then if we change the bases to v plus w and v minus w, then v is gonna have this gram matrix. And why is that? Well, this just means this entry 0 here implies that v plus w, b of v plus w with itself is 0. And let's see why. So if you expand it out, then we see this is alpha, this is minus alpha by definition of v and w, and then this is 0. So this is whole thing gonna be 0. And then the entry 2 alpha here means this cross term v plus w. When we take that to pair that with v minus w, we should get 2 alpha, and that comes from the difference of square. So why does this mean that v must be isometric to the hyperbolic plane? Well, we can just shrink one of these basis element, then this diagonal entry will have to shrink. We can always shrink it to get it to be equal to 1. So we see that this space is isometric to the hyperbolic plane, and thus we see that a binary quadratic space is isometric to the hyperbolic plane if and only if its discriminant is -1.